Somewhere in our galaxy, a single spoonful of matter weighs more than every mountain on Earth combined. It spins 700 times a second. Its magnetic field could tear the atoms out of your body from half the distance to the moon. Tonight we go inside this object. You'll meet a quake that outshines the sun for a full year, a soup of particles that flows without friction, and a core so strange physicists aren't sure what to call it. If this kind of journey keeps you up at night, subscribe and stay with us. Take a breath. We're going in. Hold out your hand. Imagine a teaspoon resting in your palm. Now imagine that teaspoon weighs as much as every mountain in the Rocky Range stacked together. Your arm doesn't just drop. The spoon punches straight through your hand, through the floor, through the crust of the Earth, and keeps going. That is 1 teaspoon of neutron star. To understand why, we have to talk about empty space. You think of yourself as solid. You feel solid. But almost all of you is nothing. An atom is about 99.9% empty. If you scaled the nucleus of an atom up to the size of a marble and placed it at the center of a football stadium, the electrons would be buzzing somewhere out near the cheap seats. Everything in between is void. That void is what lets you exist as a fluffy, low-density creature. A neutron star removes the void. Picture a trash compactor, but one that works at the atomic level. Squeeze an atom hard enough, and the electrons get rammed into the protons. The electrons and protons merge and become neutrons. Now all those empty stadiums collapse down to the marble at the center. Every atom becomes just the nucleus, and every nucleus sits pressed directly against the next one, packed so tightly there is no gap at all. The result is matter at its absolute limit of crowding. A sugar cube of this stuff weighs about 1 billion tons. That's roughly the weight of every human being on the planet, pressed into something you could balance on your fingertip if your fingertip could survive the experience, which it cannot. Let me give you a better picture. The state of Texas is big. It's about 270,000 square miles. If you somehow compress the entire state of Texas, including every building, every highway, every person, every grain of soil down to the density of a neutron star, the whole thing would fit inside a grain of rice. A single grain. Now zoom back out. A neutron star is a ball only about 12 miles across. You could drive across it in 15 minutes if driving across it didn't kill you in the first nanosecond. That tiny ball contains more mass than our sun, sometimes twice as much. Think about what the sun is. The sun holds all 8 planets in orbit. The sun is so big you could line up 109 Earths across its face. And we're saying take that entire furnace and shrink it down to the size of a small city. The density inside goes beyond anything we can build, simulate, or directly test. The strongest magnets on Earth can't produce the pressure at the surface. The most powerful particle accelerators can't recreate conditions a single inch below the crust. We can stare at neutron stars through telescopes. We can listen to them ripple through gravitational waves, but we cannot touch the inside of one. Every model we have is a guess informed by mathematics and a few precious signals from the sky, and yet we know this much for certain. Somewhere out there, right now, objects exist where the rules we live by quietly break down. What gets even harder to accept is how these things are born. Because to make one, a star has to die in a very particular, very violent way. A massive star spends millions of years burning, and then, in less than 1 second, it ends. Here is what happens in that second. Picture a star about 20 times heavier than our sun. For most of its life, it's doing a slow, stable dance. Deep in its core, hydrogen atoms are smashing together to make helium, and that fusion releases enormous energy pushing outward. Meanwhile, the star's own gravity is pulling everything inward. The outward push and the inward pull balance out. The star holds its shape. Now, the hydrogen starts to run out. The core shrinks and gets hotter. Hot enough that helium begins fusing into carbon. When the helium runs out, carbon fuses into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each new fuel burns faster than the last. Hydrogen took millions of years. Silicon burns through in about a day. Then the core reaches iron, and everything stops. Iron is the problem. Every element lighter than iron releases energy when it fuses. That energy is what keeps the star puffed up against its own gravity. But iron is different. Fusing iron doesn't release energy. It absorbs energy. So the moment the core fills up with iron, the furnace goes cold. The outward push vanishes. Gravity has been patient for 10 million years. Now it wins. The core collapses, and it does not collapse gently. We're talking about a ball of iron the size of Earth falling in on itself at roughly a quarter of the speed of light. In less time than it takes you to blink, that iron ball gets crushed down to the size of a small city. The temperature at the center spikes to over 100 billion degrees Fahrenheit. That is thousands of times hotter than the center of the sun. At those temperatures, the iron atoms themselves break apart. Protons and electrons are squeezed so hard that they fuse into neutrons. A flood of ghostly particles called neutrinos pours out, carrying away more energy in 10 seconds than our sun will release in its entire lifetime. Meanwhile, the outer layers of the star, millions of miles of gas and plasma, are still falling inward, not realizing the floor just disappeared. They crash down onto the newly formed neutron core, and the core, now impossibly stiff, refuses to compress any further. The infalling material bounces. That bounce is the supernova. A shockwave rips outward, tearing the star to pieces, blasting its guts across space at thousands of miles per second. For a few weeks, this single dying star outshines every other star in its galaxy combined. If it happened close enough to Earth, you could read a book by its light at midnight. When the fireworks fade, something is left behind. A tiny, dense remnant sitting at the exact spot where the core used to be. Still hot, still spinning, still cooling. This is the newborn neutron star. It came into existence in under a second. It will now sit there, radiating quietly, for billions of years. But something strange happened during that violent birth. The particles inside got rearranged in a way that nothing on Earth has ever experienced. The protons and electrons are gone. Something else has taken their place. Inside the new neutron star, something impossible has happened to the atoms. The protons are gone. The electrons are gone. Only neutrons remain, packed shoulder to shoulder in a way that should not be physically allowed. To understand why, we need to talk about a rule of nature that keeps everything you know from collapsing. The rule is called the Pauli exclusion principle. It sounds technical, but the idea is simple. Certain particles, including electrons, refuse to share the same state. If one electron is sitting in a specific spot doing a specific thing, another electron cannot sit in that exact same spot doing that exact same thing. They push each other away, not because they dislike each other, because the laws of physics forbid it. This refusal creates pressure, a real physical pressure that has nothing to do with heat or motion. It exists even at absolute zero. Physicists call it degeneracy pressure, and it is what holds up your chair, your body, and your planet against gravity. Now back to the collapsing core. When gravity pushes hard enough, The electrons get crammed closer and closer. They fight back with their exclusion principle pressure. For a while, that's enough. Small dead stars called white dwarfs stop their collapse right here. The electrons hold the line, and the whole star settles into a stable ball the size of Earth. But in a massive star, gravity keeps pushing harder, past the point where electron pressure can handle it. At that point, the electrons do something desperate. They start merging with the protons. This is called inverse beta decay, and it works like this. An electron and a proton slam into each other. They fuse. What comes out is a neutron, plus a tiny neutral particle called a neutrino that zips away at nearly the speed of light. One electron plus one proton equals one neutron. Both charges cancel out. The result is electrically neutral, which is where the neutron gets its name. Trillions of these mergers happen at once. The core is flooded with neutrinos pouring out into space. And in the space of about a second, almost every proton and every electron in the core has been converted into a neutron. Think about what this means. The ordinary building blocks of matter, the ones that make up every atom of you, every rock, every star, have been erased and replaced. Where there were once separate positive and negative particles orbiting each other in mostly empty space, there is now a solid mass of one single type of particle, touching. And here's the astonishing part. The Pauli exclusion principle still applies, but now it's the neutrons that refuse to share states. They push back against gravity with their own version of degeneracy pressure, far stronger than the electron version because neutrons are much heavier. This neutron pressure is what finally stops the collapse. The star grinds to a halt. It is now a solid wall of neutrons, resisting further crushing through a purely quantum mechanical effect. Nothing on Earth contains matter like this. Not the deepest ocean, not the core of any planet, not even inside an atomic bomb. This state exists only in dying stars, and on top of that wall of neutrons something even stranger forms. A crust, a surface, solid ground, but solid in a way you've never imagined. The outer shell of a neutron star is solid. You could, in principle, stand on it. You would be vaporized, crushed, and torn apart by gravity in that order, but the ground beneath you would be firm. What makes this crust strange is how it's arranged. On Earth, solid materials are solid because their atoms lock together in patterns. Salt forms cubes. Diamond forms a rigid three-dimensional cage. Ice forms hexagons. These patterns are called crystal lattices, and they give materials their hardness, their shape, and their ability to crack along certain lines. A neutron star has a crystal lattice too, but instead of atoms, the building blocks are atomic nuclei. Just the nuclei. No electrons circling them the way they would on Earth. Those electrons are stripped off and floating freely through the material, like a sea. Picture a warehouse floor covered in evenly spaced marbles. Those marbles are the nuclei. Now imagine the air above the floor is swimming with tiny bees, and those bees are the electrons. The bees can go anywhere. They aren't attached to any specific marble, but the marbles themselves sit in a rigid grid, unable to move. This arrangement creates a material roughly 10 billion times stronger than steel. Let that number settle for a moment. 10 billion times. If you made a cable out of this stuff as thin as a human hair, you could use it to tow the moon. A sheet the thickness of a sheet of paper could stop a bullet without flexing. A hammer striking a neutron star crust would shatter long before it left a dent. As you go deeper into the crust, the nuclei themselves change. At the surface, you find iron, or sometimes nickel, normal stuff. But a few feet down, the pressure starts distorting the nuclei. They get heavier. They absorb more neutrons than they should be able to hold. At Earth's pressures, these nuclei would instantly fall apart. Here, they are stable, because there is nowhere for their pieces to go. A mile or so below the surface, the nuclei are so bloated with neutrons that they start leaking. Individual neutrons begin dripping out, drifting between the lattice points. The material becomes a strange hybrid, solid nuclei holding position in their grid, while a separate fluid of free neutrons flows through the gaps between them. Think of a sponge soaked in water. The sponge keeps its shape. The water flows freely through the holes. A neutron star crust at this depth works the same way. The crystal is the sponge, the neutrons are the water, and the mountains on this crust are strange too. Because the surface gravity is so punishing, nothing can stick up very high. The tallest possible mountain on a neutron star is less than an inch tall, below the scale of your fingernail. Yet because of the density, even that tiny bump holds more mass than Mount Everest. The crust is less than a mile thick, wrapped around a mass twice the Sun's. It is the final barrier between the outside universe and the strange ocean below. Sometimes, under enough strain, that barrier fails. The crust cracks, and when it cracks, something happens that briefly outshines almost anything else in the sky. On December 27, 2004, instruments across the solar system suddenly flinched. Satellites saw a blinding flash. The upper atmosphere of Earth, the ionosphere, visibly lurched as if something had slapped it. For 0.2 of a second, this flash was brighter in gamma rays than the full moon is in visible light, even though the source was 50,000 light-years away, on the far side of our galaxy. A neutron star had cracked. The star is called SG 1806-20. It is a type of neutron star called a magnetar, which we'll meet in detail later. For now, here's what happened. The crust of this star is being wound up tighter and tighter by its own insane magnetic field. The stresses build. The solid lattice starts to strain. Eventually, something gives. When the crust of a neutron star fails, the energy released is difficult to describe in ordinary units. In that 0.2 of a second, this one flare emitted more energy than our sun will radiate over the next 250,000 years. Combined, all at once, from an object 12 miles wide. Physicists call these events starquakes. The word makes it sound like an earthquake. It is not an earthquake. An earthquake on Earth shifts the ground by a few feet at most. A starquake on a neutron star might shift the surface by about 1 millimeter. Not a meter, a millimeter. And yet that tiny shift releases the energy of 1,000 stars because the crust is so absurdly dense and so absurdly stressed. Let me put that differently. If the crust moves the width of a human hair, the shockwave can be detected across the galaxy. Here's how the mechanism works. The magnetic field of one of these stars is anchored in the crust. As the field slowly rearranges itself, it tugs on the lattice below. The lattice resists because it is 10 billion times stronger than steel. For decades, maybe centuries, the stress builds. Then, at some critical point, the lattice fractures. Entire plates on the surface shift. The magnetic field suddenly snaps to a new configuration, and the leftover energy blasts out as a gamma-ray flare. The 2004 event was the most powerful flash of energy ever recorded from outside our solar system. Nothing before or since has beaten it. It was so bright that scientists had to go back and recalibrate their detectors. The instruments weren't designed to handle a signal that loud. Several of them saturated, meaning they hit their maximum reading and stayed there while the flare continued. And the ionosphere of Earth, 50,000 light-years away, was briefly disturbed by it. The upper layer of our atmosphere was pushed around by a burp from a dead star on the other side of the galaxy. If a similar starquake had happened within a few light years of Earth, it would have stripped our ozone layer and caused a mass extinction. These events are rare. We've only seen 3 of this scale in modern history, but they tell us something crucial about what's under the crust. Because the way the star rings after a quake, the tiny vibrations that follow, behaves very differently from a normal solid. The inside isn't behaving like rock, it's behaving like something that shouldn't exist. Below the crust of a neutron star, the lattice ends. There is no bedrock, no deeper layer of rock or metal. Instead, there is an ocean. But the word ocean is misleading. There is no water, there are no molecules, there are no atoms. There is only a fluid of free neutrons flowing through space in a state no substance on Earth has ever achieved. Imagine taking every drop of water in the Pacific Ocean and replacing it with pure nuclear matter, packed with the density of an atomic nucleus, all the way down. That's the kind of ocean we're describing, except it's not miles deep, it's hundreds of millions of miles deep, in the sense that if you could somehow hold one drop of it in your hand, the gravitational pull of that drop would be unimaginable. This ocean forms at a very specific depth. About a mile below the surface, the nuclei in the crust are saturated with neutrons. They can't hold anymore. Push them any harder, and the neutrons start leaking out and flowing between the nuclei. Go a little deeper, and the nuclei themselves dissolve entirely. What remains is a pure neutron fluid. To understand how weird this is, think about normal matter. Everything you have ever touched is held together by electromagnetic forces, atoms bonding to atoms through the push and pull of a sectric charge. Remove the charges and ordinary matter falls apart instantly. Neutrons have no charge. They cannot bond electromagnetically. On Earth, a free neutron outside an atomic nucleus lives for about 15 minutes, and then decays into a proton, an electron, and a neutrino. You cannot bottle neutrons, you cannot stockpile them, they break down. Yet inside a neutron star there are oceans of them, stable, lasting for billions of years. How? The answer is that the ocean exists under conditions so extreme that decay becomes impossible. A neutron normally decays because it can drop into a lower energy state by becoming a proton. But inside this ocean, every available proton slot is already taken. There is nowhere for a decaying neutron to go. The Pauli exclusion principle, the same rule that packs the neutrons together in the first place, also locks them in. They can't decay because the exit door is full, so they stay. Trillions upon trillions of them, flowing through a space the size of a city. The pressure at the top of this ocean is already roughly 10 trillion times the pressure at the bottom of the Mariana Trench on Earth. The deepest trench on our planet would be considered a perfect vacuum by comparison. Heat at this depth reaches hundreds of millions of degrees, though the ocean has no way to conduct that heat in any familiar sense, and there is something else happening down here. Something that took physicists decades to accept as real. The ocean is doing things fluids aren't supposed to do. It flows through itself with zero resistance. It spins in patterns that never slow down. Stir it, and the stirring continues forever. The normal rules of friction, the rules that eventually bring all motion to a halt, simply don't apply here. This ocean is alive in a strange way. It is a superfluid, and once we understand what that actually means, the inside of a neutron star gets even stranger. On Earth, if you stir a cup of coffee, the swirl slows down and stops. That slowing is friction. Every fluid you have ever touched has friction. Water has it. Oil has it. Even liquid nitrogen has it. But there is one substance on Earth that does not. If you cool helium to about 456 degrees below 0 Fahrenheit, something strange happens. The helium changes. It becomes a superfluid. Stir it, and the stirring continues, apparently forever. Pour it, and it can climb up the walls of its container and escape over the top. Squeeze it through a pinhole and it flows through without any pressure at all. Inside a neutron star, this same phenomenon happens on an almost unimaginable scale. The ocean of free neutrons behaves as a superfluid. Here is how physicists figured this out. They weren't there, they couldn't take samples, but they could watch the star spin. Pulsars, which are a type of neutron star, rotate with astonishing regularity. Some of them tick more reliably than atomic clocks. You can set your watch by them. Over decades, their spin slowly winds down, like a top running out of energy. This gradual slowdown is predictable and smooth, except every once in a while the star hiccups. Without warning, a pulsar will suddenly speed up, tiny amounts, maybe 1 part in a million. Then it will settle back into its smooth deceleration. These events are called glitches, and for a long time nobody could explain them. The answer, it turns out, involves the superfluid ocean. The outer crust of the star is a solid that rotates like any normal solid. It slows down over time because its magnetic field drags against the surrounding space. But the superfluid inside doesn't slow down. It can't. A superfluid has no friction, so nothing is there to rob it of rotation. Imagine a spinning coffee mug where the mug itself is slowing down, but the coffee inside keeps spinning at the original speed. Eventually the mismatch gets too big. The superfluid has to transfer some of its rotation to the crust. It does this in sudden bursts, spinning the star up slightly before settling back down. Every glitch we detect is evidence that the ocean below is a superfluid, turning frictionlessly beneath the ground. The physics gets stranger from here. A superfluid cannot rotate the way an ordinary fluid does. You can't just swirl it around. Instead, when you try to make it spin, it forms tight little whirlpools called vortices. Each vortex is essentially a microscopic tornado of rotating neutron fluid. A neutron star spinning at hundreds of revolutions per second contains roughly 1 billion of these vortices, arranged in a neat triangular grid beneath the crust. Picture a forest of invisible tornadoes, each one spinning at incredible speed, each one perfectly parallel to its neighbours, covering the entire inner surface of the star. That is what physicists think lives under the solid ground of a neutron star. When a glitch happens, some of these vortices suddenly rearrange themselves. The ocean releases a tiny amount of its angular momentum to the crust, and the whole star jumps forward in its rotation. But superfluid neutrons aren't the only strange state of matter in there. A few miles deeper, there is another fluid entirely, one made of the few remaining protons, and that fluid is doing something even harder to picture. A few miles below the crust, alongside the superfluid ocean of neutrons, lives a second fluid. This one is made of protons, and it is a superconductor. To understand what that means, picture the wiring in your house. When electricity flows through copper wire, some of that energy turns into heat. That's because the electrons carrying the current keep bumping into the copper atoms. Over miles of power line, this resistance wastes a huge amount of energy. A superconductor has no resistance. Send an electric current into a loop of superconducting wire, and the current will flow forever. In laboratory experiments on Earth, physicists have started currents in tiny superconducting rings, then walked away and come back years later to find the current still running at full strength, having lost nothing. On Earth, We achieve this only at brutally cold temperatures, close to absolute zero. Even then, it requires specific materials. Inside a neutron star, the temperature is in the hundreds of millions of degrees. By Earth logic, no superconductor should be possible there. And yet the pressure is so intense and the proton density so finely tuned that the protons fall into exactly the right pattern to pair up and flow without resistance. The result is a fluid that carries electricity forever. Now, why does this matter? Because this proton superconductor is what locks in the magnetic field of the neutron star. Every neutron star has a magnetic field. Some of these fields are merely ferocious. Others, the magnetars, have fields so strong they rearrange the atoms of anything nearby. But all of them last for millions or billions of years, which is a problem if you think about it. Magnetic fields usually decay. A bar magnet on your refrigerator will slowly lose its strength. A planetary magnetic field can flip or fade over time. The field of a neutron star does not fade. The superconducting proton fluid traps the magnetic field lines and refuses to let them go. It's as if the magnetism is frozen into the star's interior, held in place by a current that will never stop running. Here's a way to picture the whole arrangement. Imagine two different liquids poured into the same glass, occupying the same space at the same time, each one ignoring the other. One is the neutron superfluid, flowing without friction. The other is the proton superconductor, carrying current without resistance. They coexist, interpenetrating, each following its own bizarre rules. Physicists call this a two-fluid model. It's the best picture we have of what's going on in the inner layers of a neutron star, and it is very different from anything you can build or even simulate properly on Earth. The two fluids are also coupled in subtle ways. The proton superconductor forms tiny tubes that carry the magnetic field, similar to how the neutron superfluid forms tiny vortex tornadoes. These tubes and vortices get tangled together. When one fluid moves, it tugs the other. When the star tries to change its rotation, the entire interior has to negotiate what happens next. This is the plumbing of a neutron star. Frictionless fluids, eternal currents, and magnetic fields locked in place. And those magnetic fields are about to get far stranger than we've let on. A refrigerator magnet has a magnetic field of about 50 Gauss. Earth's field, the one your compass points to, is half a Gauss. The strongest magnets ever built in laboratories, the ones used to levitate frogs and accelerate particles, reach around 1,000,000 Gauss for a brief instant before they destroy themselves. A magnetaire has a magnetic field of 1,000 trillion Gauss. There is no laboratory that can produce this. There is no material that can survive it. If a magnetar the size of a small city were somehow placed halfway between Earth and the Moon, its magnetic field alone would wipe the data off every credit card on the planet and rip the iron out of your blood. A magnetar is a specific kind of neutron star, one where the magnetic field is about 1,000 times stronger than a typical neutron star and about 1,000,000,000 times stronger than anything on Earth. To understand what this does to matter, we need to zoom in on an atom. An atom is normally a spherical thing. Its electron cloud is round or close to round, puffed out evenly in all directions. The atoms in your hand look like tiny fuzzy balls. This shape is determined by the balance between the electrons and the nucleus holding them in place. Put that atom in the magnetic field of a magnetar, and the spheres get crushed. The electrons can no longer orbit freely. The field is so strong it pins them. Atoms get stretched into thin, needle-like shapes, oriented along the direction of the magnetic field. Chemistry as we know it stops working. Bonds that hold molecules together break. The familiar geometry of matter is replaced by something linear, filamentary, strange. Within about 600 miles of a magnetar, the magnetic field is strong enough to distort the atoms of your body. Your cells would come apart not because of heat, not because of radiation, but because the basic shapes of their molecules would no longer be allowed to exist. The field also does something to empty space itself. In the presence of magnetism this strong, what we think of as pure vacuum becomes optically active. Light passing through it bends in ways it shouldn't. Photons split into pairs. The vacuum effectively behaves like a transparent crystal, refracting light based on its polarization, the same way a crystal of calcite bends light. This is a prediction of quantum electrodynamics that was written down decades before we had any way to test it. Then we pointed our telescopes at a magnetar and saw it happen. Light coming off the surface is polarized exactly the way the theory predicted, meaning empty space near these stars is not empty in the normal sense. Here's another way to grasp the scale. The magnetic energy stored in a single magnetar is comparable to the total rest mass energy of a small moon. If you could somehow release that energy all at once, you would get an explosion similar to a supernova coming purely from the magnetism. We know of about 30 magnetars in our galaxy. That's out of an estimated 100 million neutron stars total. They are rare. Most neutron stars have fields that are only ferocious, not civilization-ending. But when a magnetar gets unstable, the entire galaxy hears about it, and sometimes the edge of that sound reaches Earth. The December 2004 flare from SGR 1806-20 was brief, 0.2 of a second. For that blink of time, a single dead star on the far side of our galaxy was the brightest object in the sky in gamma-ray light, outshining the full moon in reflected visible light by a similar factor in its own spectrum. And then something unexpected happened. Earth noticed. Our planet's upper atmosphere, the thin layer of ionized gas called the ionosphere, is what lets us bounce radio signals around the curve of the globe. It's a delicate thing, sensitive to flares from our sun and to the shifts of day and night. The ionosphere usually responds to local events. On December 27, 2004, it responded to a magnetar 50,000 light-years away. Instruments detected a sudden shift in the ionosphere's density. The electron content spiked. It was as though the atmosphere had been briefly shoved by an invisible hand. Radio communications across parts of the world showed glitches. Satellite detectors went haywire. Several spacecraft in orbit were temporarily blinded by the gamma rays. 50,000 light-years. Take a moment to process that distance. Light itself, travelling at roughly 670 million miles per hour, takes 50,000 years to cross it. The flash we saw had left the magnetar before the last ice age began. It crossed the dark of interstellar space, passed through countless star systems, and finally arrived at Earth in the middle of a December holiday week, and it was strong enough to tickle our atmosphere. The flare released about 10 to the power of 46 joules of energy in that 0.2 of a second. That number is hard to hold in your head, so here is a comparison. The entire energy output of the Sun over an average day is about 10 to the power of 31 joules. This flash released 1 trillion times more energy than the Sun produces in a day. 1 trillion times. A day of the Sun. The only reason we survived it without harm is distance. 50,000 light-years of empty space diluted the flare into something our planet could absorb as a hiccup. If SGR 1806-20 had been, say, a few thousand light-years away, the outcome would have been different. The ozone layer might have been badly damaged. High-energy radiation would have reached the surface. Depending on the exact distance, it could have caused a mass extinction, similar to what some physicists think may have happened in Earth's distant past from events like this. There is strong evidence that late Ordovician mass extinctions about 450 million years ago might have been triggered by a nearby gamma-ray burst, though the exact culprit is debated. The ecological collapse matches the pattern you would expect from sudden ozone depletion and a surge of ultraviolet light. For now, we are safely distant from any magnetar that could threaten us. The nearest one is thousands of light years away and showing no signs of preparing another megaflare. But the 2004 event taught us something profound. These objects are not isolated curiosities. They are active, violent participants in the story of our galaxy. Their bursts shape atmospheres, seed radiation, and occasionally reach across vast distances to touch planets they will never know exist. Before we understood magnetars this well, neutron stars had already surprised us in another way. They spoke to us in steady, regular, artificial-sounding pulses. In the summer of 1967, a young graduate student named Jocelyn Bell was reviewing strips of paper coming out of a radio telescope at Cambridge. The telescope's output was printed as squiggles on long rolls, and her job was to look for unusual patterns among miles of data. One evening she noticed something odd. A quick burst of pulses, spaced about 1 1/3 seconds apart. Click, click, click. Each pulse was extremely short, just a few milliseconds, but the regularity was eerie. Astronomical signals are supposed to be messy. Stars flicker, radio sources drift. Nothing natural ticks like a clock. But this signal ticked with machine precision, night after night, coming from the same patch of sky. For a brief period, the Cambridge team seriously considered whether they had picked up a transmission from another civilization. They even nicknamed the source LGM-1 for Little Green Men. The idea was speculative but not absurd. The signal had the regularity of something designed. Then, a few months later, Bell found a second source in a different part of the sky, ticking at a different rate, and a third and a fourth. Aliens might build one beacon. They would not build 4 in random directions at random rates. Something natural was producing these signals. Something fast, something stable, something like a clock. The answer was a neutron star, but a neutron star doing something no one had quite pictured before. A pulsar is a rapidly rotating neutron star with a beam of radio waves streaming out of each of its magnetic poles. The beam sweeps across space as the star spins, like the beam of a lighthouse. If that beam happens to cross the line of sight between the star and Earth, we see a pulse. Every rotation, one beam sweeps past us, and our telescopes pick up a flash of radio. Tick, tick, tick. The clock-like regularity comes from the rotation itself. A neutron star spinning once every second will send us a pulse every second with extraordinary precision. Some pulsars are so stable they rival atomic clocks. Astronomers have used them to test general relativity, track planetary motions, and even search for gravitational waves. Over years of observation, the best pulsars have been shown to be accurate to a few hundred nanoseconds per decade. Here's the visualization that helps. Imagine a lighthouse with 2 spotlights mounted on opposite sides. The lighthouse is spinning at high speed. If you stand somewhere, the beams will sweep over you. You see a flash twice per rotation. If they don't sweep over you, you see nothing. That's why, even though most neutron stars probably have these beams, we only detect about 1 in 10 as a pulsar. The rest are aimed in directions we can't see. Once the first pulsars were identified, telescopes started finding them everywhere. In the Crab Nebula, a pulsar was discovered sitting right at the spot where Chinese astronomers had recorded a supernova in the year 1054. The historical record and the modern observation lined up perfectly. The pulsar was the corpse of the star that had exploded nearly 1,000 years earlier. And then came the strangest pulsars of all, ones that don't tick once a second, ones that tick hundreds of times a second. There is a neutron star called PSRJ 1748-2446 AD. It's about 12 miles across, contains roughly twice the mass of our Sun, and it is rotating 716 times every second. Take a moment with that. Not 716 rotations per minute, not per hour, per second. If you could stand on the equator of this star and somehow not be instantly vaporized, you would be moving at around 70,000 kilometers per second. That's about 24% of the speed of light, a quarter of light itself. By every piece of ordinary intuition you have, this object should fly apart. Spin anything fast enough, and the centrifugal forces at its edges will tear it to pieces. A DVD spinning too fast in a player shatters. A grindstone over a certain speed explodes into shrapnel. The faster you spin something, the harder it is for the material to hold together. A neutron star doesn't care. Its gravity is so absurdly strong that even at a quarter of light speed the surface stays put. The gravitational pull at the equator of this star is about 100 billion times stronger than the pull you feel on Earth. The outward push of its rotation, the force that would hurl material into space, is a few percent of that. It is easily overpowered. The star holds together with ease. How does a star end up spinning this fast? The answer is usually a partner. Most of the fastest spinning pulsars live in binary systems, with another star close enough that they share material. For millions of years, this companion star shed gas that fell onto the neutron star. As the gas spiraled inward, it gave up its angular momentum to the neutron star, like a skater pulling her arms in and spinning faster. Over time, a slow old pulsar can be accelerated by this process until it is rotating hundreds of times per second. These are called millisecond pulsars because the time between their pulses is measured in milliseconds. What's remarkable is how quiet and stable they become. A young pulsar slows down relatively quickly, its magnetic field dragging against its environment. A millisecond pulsar has a much weaker magnetic field, for reasons tied to its history, and that means much less drag. It will keep spinning at nearly the same rate for 1 billion years, ticking off the seconds more reliably than almost any clock humans have built. We use these clocks. Astronomers have assembled networks of millisecond pulsars and time their signals from Earth over decades. The tiny deviations in arrival time can reveal gravitational waves rolling through our galaxy, waves too slow and massive to be caught by other detectors. In 2023, a network of pulsar timing arrays announced the first evidence of a background of gravitational waves, likely produced by pairs of supermassive black holes merging across the universe. Those signals were read out of the ticking of dead stars. Not every neutron star can be sped up like this. There is a speed limit. Physicists believe that above a certain spin rate, even a neutron star would start to shed material from its equator. The exact limit depends on what the inside of the star is made of, which, as we've seen, is a subject of fierce debate. The universe, it turns out, will not let these stars get heavier than a certain amount either. Push past that mass, and something far worse happens. Neutron stars come in a range of masses. The lightest ones we know about are a little over 1 solar mass. The heaviest confirmed one is roughly 2¼ solar masses. Above that, things get theoretical. Physicists believe there is a hard ceiling. Somewhere between 2 and 2.5 solar masses, a neutron star can no longer support itself. Pile any more mass on top of it, and it collapses. Not into a denser neutron star, into a black hole. This ceiling has a name. It's called the Tolman-Oppenheimer-Volkoff limit, named after the 3 scientists who first calculated it back in the late 1930s. Finding the exact value is one of the central puzzles of modern astrophysics, because it tells us what the inside of a neutron star is actually made of. Here is why. The higher the limit, the stiffer the interior must be. A stiff interior pushes back harder against gravity, allowing the star to hold more mass without collapsing. A soft interior gives in more easily and sets a lower ceiling. So if we can pin down the precise maximum mass, we have a direct clue about what kind of exotic matter exists in the core. For decades, theorists went back and forth. Some models predicted the limit should be around 1.5 solar masses, others argued 2. A few optimistic models pushed it to 3. Different assumptions about how the neutron fluid behaves, or whether something weirder replaces it in the core, gave wildly different answers. Then in 2010, astronomers discovered a neutron star with a mass just under 2 solar masses. 2 years later, another at almost exactly 2. In 2019, a pulsar in a binary system was carefully weighed and came out at about 2.14 solar masses. Every time the mass record broke, a bunch of theoretical models were immediately ruled out. The interior had to be stiff enough to support these observed masses. Softer models of the core were falsified. But there is a twist. Black holes have a minimum mass too, or at least they should in most theories of how they form. The smallest black holes that emerge from stellar collapse are around 5 solar masses. Between 2.5 and 5 solar masses, there is a gap. No one knows what lives in that gap. Are there neutron stars that stretch the theoretical maximum? Are there objects that are not quite neutron stars and not quite black holes, held up by some state of matter we haven't named? Are some of the small black holes we detect actually not black holes but something weirder? These are open questions. Recent gravitational wave detections have started filling in this gap. In 2020, a merger event involved an object of about 2.6 solar masses. Was it the heaviest neutron star ever, or the lightest black hole ever? The data isn't clear enough yet to say. The discovery of that one event was important enough that it reopened debates physicists thought were settled. The mass limit isn't just a number on a chart, it's a doorway. Cross it and gravity wins. The star falls inward and never stops. No quantum pressure, no lattice, no strange fluid is strong enough to hold it up. What happens at the exact moment of crossing is something physics still struggles to describe. Imagine pushing down on a neutron star with more and more mass. The crust compresses. The ocean below gets denser. Every quantum trick the star can play to hold itself up gets strained to its absolute limit. At some point, the neutrons themselves can no longer do the job. Neutron pressure is powerful, but it is finite. The degeneracy pressure that holds these stars up is a purely quantum effect, and like all forces, it has a maximum. Once gravity exceeds that maximum, there is nothing left to catch the star. It begins to collapse again, the way it did when it was first born, except this time no new state of matter rises to stop it. Or maybe something does. That's the part we don't know. Picture the pressure graph inside a neutron star as a staircase. At the top, ordinary nuclei in the crust. A few steps down, atomic nuclei drip in with neutrons. A few more steps, pure neutron ocean, superfluid and superconducting. At the deepest levels, the steps become uncertain. Theorists have drawn many different possible staircases, and they all fit the data we have, but they branch off at the bottom. Some models say the neutrons just keep being neutrons, all the way down to the centre. If that's true, the maximum mass for a neutron star works out to one specific value, and the collapse into a black hole happens as soon as that value is exceeded. Other models say something else happens before collapse. The neutrons break down into their constituent parts. Because neutrons aren't fundamental particles, they're made of smaller things called quarks, bound together by the strongest force in nature. Under ordinary conditions, quarks are locked inside neutrons and protons. You cannot pull them out. The force binding them actually gets stronger the farther apart you try to pull them, which is the opposite of how gravity or electromagnetism work. Quarks are the prisoners of their own cage. Under enough pressure, the cage might break. Some theorists calculate that at the very centre of a neutron star, where pressures reach a few times 10 to the power of 35 pascals, the neutrons start to overlap. Their boundaries blur. The quarks inside them are no longer confined to individual neutrons. They flow freely, forming a soup of unbound quarks. This is called deconfined quark matter, and it would be the fourth phase of matter we have discussed inside a single star. Ordinary crust, neutron fluid, proton superconductor, and now a quark soup. All stacked on top of each other in a ball 12 miles wide. The existence of quark matter in neutron stars is not confirmed. It is a theoretical prediction that fits some models better than others. Recent gravitational wave observations and precise mass measurements are slowly narrowing the possibilities, and some physicists believe the evidence is starting to lean toward quark matter being real, at least in the heaviest neutron stars. If it is real, then there is a strange hybrid object hiding among the ordinary neutron stars. An outer shell of crust, an ocean of neutrons, and a core of something truly alien. Physicists call these hybrid stars, and there might be an even stranger possibility. Objects where the entire interior, not just the core, is made of quark matter. But before we meet those, there is a stop along the way. A layer of matter so geometrically strange that physicists nicknamed it after food. Right at the boundary between the crust and the ocean, something unexpected happens. Nuclear matter, which is normally blob-shaped in the nuclei of atoms, starts rearranging itself into geometric patterns. Physicists noticed this in simulations decades ago, and the shapes it forms are so specific and so odd that they ended up being named after pasta. This layer is called the nuclear pasta phase. Here's how it works. In the outer crust, you have distinct atomic nuclei surrounded by empty space. The nuclei sit at positions in the lattice, and between them is vacuum filled with free electrons. As you go deeper, the nuclei get closer together. They swell. They merge. At a certain depth, the nuclei can no longer maintain their spherical shape. The competing forces of attraction and repulsion between them create new geometries. First, the nuclei squish into flat disks, like lasagna noodles stacked on top of one another, layers of nuclear matter with layers of neutron fluid between them. Repeating, like pages in a book. This is the lasagna phase. Then the disks break up into long cylinders, lying parallel to each other, tubes of dense nuclear matter suspended in the surrounding fluid, arranged in irregular grid. This is the spaghetti phase. Below that, the cylinders merge in some places and break in others, forming a sponge-like network. This is called the gyroid, or anti-spaghetti phase. Eventually, the geometry inverts entirely. Instead of lumps of nuclear matter in a neutron sea, you get bubbles of neutron sea trapped inside a sheet of continuous nuclear matter. Every one of these shapes exists in a thin layer, maybe a few hundred yards thick, at the boundary between crust and ocean. You could walk through several pasta phases in the time it takes to walk across a football field. Why does matter do this? It's the same reason soap bubbles form spheres and honeycombs form hexagons. Under specific conditions, certain geometries minimize the total energy of the system. Nuclear matter at these densities has several competing energy contributions: surface tension, electrical repulsion, neutron pressure, and when you balance them all, the shapes that come out are rods and sheets and tubes rather than simple spheres. What does pasta do for the neutron star? A few things. It changes how heat and sound travel. It affects the magnetic field. Most importantly, it may help explain why neutron stars release their heat in very specific ways. Young neutron stars cool faster than some models predicted, and the pasta layer may be acting like an insulator that traps heat in certain regions and lets it escape in others. Recent simulations suggest that the pasta phase may be the single strongest material in the universe, even stronger than the regular crust. 10 billion times the strength of steel might be an underestimate for what happens right at the boundary layer. If you could somehow extract a cubic inch of the pasta phase and bring it to Earth, it would weigh about as much as a large skyscraper and be so stiff that you could not dent it with any force humans can generate. Assuming it didn't instantly vaporize you, which it would, below the pasta the ocean takes over, and below the ocean, in the deepest heart of the star, physicists suspect the neutrons are coming apart. Near the center of a sufficiently heavy neutron star, the pressure reaches a point where neutrons stop being neutrons. A neutron is a bound state of 3 quarks, 2 quarks of one type, one of another. These quarks are held together by a force carried by particles called gluons, and this force is so strong that pulling the quarks apart normally requires more energy than the universe can easily provide. Quarks are glued inside their neutrons and protons, and that's supposed to be that. But squeeze a neutron star core hard enough, and the neutrons start overlapping. Their boundaries blur. The quarks inside one neutron can no longer tell which neutron they belong to. They start behaving as a shared soup of free quarks and gluons, unbound and flowing as a single fluid. This is called quark matter. It is the phase of matter that existed microseconds after the Big Bang, before the universe cooled enough for quarks to be locked inside protons and neutrons. If it exists inside neutron stars today, then the cores of these stars contain a relic of the earliest moments of the universe, pressed into a stable form by sheer gravity. The transition from neutron matter to quark matter is not sudden. Physicists imagine a gradual shift where first a few quarks become unbound, then more, then eventually the whole core becomes a uniform quark soup. Depending on the details, this transition could happen over a thin boundary or gradually across a thick shell. There are also flavors of quark matter. The lightest quarks are called up and down. Ordinary neutrons and protons are made entirely of these two flavors, but at high enough densities, a third type of quark called strange can start appearing spontaneously. Strange quarks are heavier than up and down quarks, and normally they don't show up in stable matter because it takes energy to make them. In the core of a neutron star, the pressure is so intense that making strange quarks might actually be energetically favorable. The matter relaxes into a state that mixes up, down, and strange quarks in roughly equal proportions. This is called strange quark matter. If strange quark matter is more stable than ordinary matter, which some physicists suspect, then the implications are unsettling. It would mean that ordinary matter is actually in a metastable state, and that under the right conditions it could convert into strange quark matter and release energy in the process. nobody has directly observed quark matter in a neutron star. But the gravitational wave signature of a neutron star merger depends sensitively on the equation of state inside, and recent observations are beginning to show patterns consistent with quark matter in the heaviest stars. Here's a visualization to carry with you. Think of the center of a 2 solar mass neutron star as a region about the size of a large city. Inside that region, trillions of quarks are flowing as a single fluid. No individual neutrons, no individual protons, just a flowing hot plasma of fundamental particles held in place by the gravity of more than 1 million Earths worth of mass sitting on top of it. If strange quark matter exists and is truly stable, then there may be objects in the universe where the entire star, not just the core, is made of this stuff. Those would be strange stars, and if one of them ever touched Earth, the consequences could be catastrophic. In 1984, a physicist named Edward Witten published an idea that haunts the field to this day. He suggested that strange quark matter, the soup of up, down, and strange quarks we met in the last chapter, might not just exist inside neutron stars. It might be the true ground state of all matter. That sounds like a technical detail. It isn't. If Witten is right, then ordinary atoms, the carbon and oxygen and iron that make up you and your planet, are not the lowest energy form matter can take. They are a high-energy arrangement that is stable only because the path to the true lowest energy is blocked. To get from ordinary matter to strange quark matter, you need to convert up and down quarks into a mix with strange quarks, and that conversion requires a seed. A small piece of strange quark matter to start the chain. Inside a neutron star, that seed exists naturally because of pressure. Outside of a neutron star, there is no way to create one under normal conditions. So ordinary matter sits safely in its metastable state, forever, because nothing triggers the change. Unless a chunk of strange quark matter somehow escapes from a neutron star. A hypothetical small piece of strange quark matter is called a strangelet. The size can range from microscopic, just a few quarks, up to macroscopic, the size of a grain of sand or larger. The small ones are quickly destroyed by radiation. The large ones might be stable. Now imagine a stable strangelet drifting through space, and imagine it eventually falling onto a planet, onto Earth, say. When it touches ordinary matter, the contact triggers conversion. The first layer of atoms in contact with the strangelet gets absorbed. Up and down quarks in the atoms get converted into the up-down strange mix. The strangelet grows. It absorbs more matter. It grows again. If the conversion is energetically favorable and fast, it could sweep across the Earth in seconds to hours, converting the entire planet into a ball of strange quark matter the size of a small mountain, while releasing the surplus energy as a burst of radiation. The Earth, as a habitable planet, would cease to exist. This is worth pausing on, not because it's likely, it probably isn't, but because the math has not been fully ruled out. A few arguments suggest strangelets are probably not catastrophic. First, if they were, and if they existed in large numbers in the universe, they should have converted many ordinary stars and planets by now. We don't see evidence of this happening. Second, most strangelets that leak out of neutron stars are likely too small to be stable, and they decay back into ordinary particles before they can seed anything. Third, the energy barrier to triggering the conversion might be higher than the simplest models suggest. These arguments are reassuring but not proof. When physicists debated whether the Large Hadron Collider could accidentally create a dangerous strangelet, the consensus was no, but the discussion was serious and extended. A strange planet would have a surface of incredible density and magnetic properties we cannot predict. It would likely be invisible at ordinary wavelengths, but extremely bright in gamma rays or neutrinos. Some astronomers have even proposed searching for strange planets by looking for anomalous gravitational signals in the galaxy. And there is an even more unsettling possibility. Strange matter might not just form planets, it might form entire stars. If strange quark matter is stable on its own, without needing the pressure of a surrounding neutron star to hold it together, then an entire star could be made of the stuff. Not a neutron star with a strange core, a strange star all the way through. From the outside, a strange star will look almost identical to a neutron star. Same rough size, around 12 miles across. Similar mass, 1 to 2 solar masses. Similar rotation, similar magnetic field, similar surface temperature. If you pointed a telescope at one, it would look like another entry in the catalogue of neutron stars we've been studying for 50 years. The differences would only show up in the details. A normal neutron star has a crust, a real, solid, mile-thick layer of crystalline nuclei. A strange star might have no crust at all, or only a very thin one. The reason is that strange quark matter is self-bound. It holds itself together, unlike a gas or liquid, which requires external pressure to stay together. A droplet of strange quark matter can float in vacuum indefinitely without dispersing. A strange star could have a sharp edge. You could, in principle, have strange matter on one side of a boundary and empty vacuum on the other. This sharp edge would change how the star behaves in small ways that astronomers can potentially detect. The star would cool differently. It would respond to earthquakes differently. Its radius would scale differently with mass than a normal neutron star. And its maximum possible mass might be different. For years there have been hints. A few neutron stars observed by telescopes have radii that seem slightly too small for standard neutron star models. Others cool faster than expected. None of these anomalies are proof, but they are consistent with some of the stars we catalogue as neutron stars, actually being strange stars in disguise. Recent observations with an instrument called NISA mounted on the International Space Station have measured the radii of several neutron stars more precisely than ever before. The results so far have narrowed the range of possibilities but haven't settled whether strange stars are among them. Some measurements favour stiffer equations of state, which makes exotic interiors less likely. Others leave room for strange matter. There is also a theoretical question about how strange stars could form in the first place. Ordinary supernovae produce neutron stars. To get a strange star, you might need a trigger that converts a neutron star into strange matter, partway through its life. This could happen if a seed of strange quark matter forms spontaneously in the core and then spreads outward, eating the entire neutron star from the inside. The conversion would release an enormous burst of energy and neutrinos, producing a signature that astronomers might be able to catch with gravitational wave detectors or neutrino observatories. Nobody has confirmed that such a conversion has ever been observed, but if it happens, even rarely, then the universe contains a population of these strange stars that masquerade as their more ordinary cousins, waiting for better instruments to reveal them. If you ever stood in front of a strange star, you would see the same blazing point of light you would see from a neutron star. The difference would be hidden at the smallest scales, in the way its surface touches vacuum without a transition layer. But even strange stars are not the end of the ladder of density. Below their surfaces, something even more exotic may form. A phase of matter with a name that sounds like it belongs in a chemistry textbook. In the deepest cores of neutron stars, physicists suspect the quark matter we've been discussing organizes itself into an even stranger state, one that has no counterpart anywhere in our experience and no practical way to be produced on Earth. It is called a color superconductor. The name needs explaining. In physics, the strong force that holds quarks together is sometimes compared to electric charge, but with 3 types instead of 2. Physicists picked 3 colors, red, green, and blue, to label these 3 types. The names have nothing to do with actual colors. They are just labels. The rule is that quarks combined into a neutron or proton must balance all 3 colors, producing a net of 0 color, the way red, green, and blue lights combine into white. A color superconductor is a state where quarks pair up in a specific way that makes the strong force behave like a superconductor for color charge. Just as ordinary superconductors carry electric current without resistance, a color superconductor carries color currents without resistance. This happens because quarks, like electrons, can form pairs under the right conditions. In an ordinary superconductor, 2 electrons bind loosely into what's called a Cooper pair. These pairs can flow through a material without scattering off atoms, which is why a superconductor has no electrical resistance. In a color superconductor, quarks bind into pairs through the strong force, and the resulting fluid has exotic properties. There are different ways the quarks can pair up, and each gives a different phase of color superconductor. One version is called color flavor locked matter, or CFL. In CFL, quarks of different colors and different flavors pair up in a specific symmetric pattern, producing a state that is astonishingly orderly, despite being at unimaginable temperatures and pressures. Here's what makes it weird. In ordinary matter, temperature scrambles things. The hotter you make something, the more disorganized the particles become, randomly bumping around. Color superconductors manage to stay organized even at temperatures of billions of degrees, because the pairing is enforced by the strong force and requires enormous energy to break. If the cores of the heaviest neutron stars contain color superconducting matter, then the insides of these stars are simultaneously extraordinarily hot and extraordinarily organized. A fluid where the fundamental particles are locked into coordinated patterns at temperatures that would instantly vaporize anything we know how to build. Color superconductors would affect the cooling rates of neutron stars and the behavior of their magnetic fields. Detailed models predict signatures that could be searched for in X-ray observations and in the late-stage gravitational wave signals from neutron star mergers. Picture the interior of a neutron star as a series of nested shells. Outer crust, inner crust with its pasta, ocean of neutron superfluid and proton superconductor, transition region, and finally a core that may be color superconducting quark matter. Each shell is a phase of matter stranger than the one above, and all of it is compressed into a ball the size of a small city. We can't see any of this directly. We can only measure tiny effects from outside and infer what must be happening inside. One of those effects has to do with light itself. Near a neutron star, light doesn't travel in straight lines the way it usually does. Point a flashlight at a wall, the beam goes straight. Light, as far as your eyes are concerned, moves in lines. Near a neutron star, that rule breaks. The gravity of a neutron star is strong enough to bend light by a significant amount. Not by a tiny fraction of a degree, as happens when starlight grazes our sun, by tens of degrees, enough that if you stood at a safe distance from a neutron star and looked at it through a telescope, you could see parts of the surface that are supposedly facing away from you. This isn't a trick, it isn't a reflection. The light from the backside of the star actually reaches you, bent around the gravitational well. Imagine the star as a ball sitting on a stretched rubber sheet. pulling the sheet downward into a deep funnel. A marble rolling across the sheet will curve around the funnel. Light behaves the same way. The light from the far hemisphere of the star takes a curved path, bending around the star, and ends up reaching your eyes as if it had come from the near side. If you could somehow see a neutron star in detail, you would see more than half of its surface simultaneously, maybe as much as 80%. A planet's backside is normally hidden from view. A neutron star doesn't have a fully hidden backside, not from any viewing angle. This gravitational lensing has practical consequences for astronomy. When a pulsar spins, one of its magnetic poles is pointed toward us part of the time and away from us other parts. Naively, you would expect to see a single flash every rotation when the pole points our way. But because of light bending, the pulse we see gets shaped by gravity in measurable ways. The shape of the pulse depends on the mass and radius of the star. By measuring pulse shapes very carefully, astronomers can work backward and figure out the star's dimensions. This is how NICA, the X-ray telescope on the International Space Station, measures neutron star sizes. It watches hotspots on the surface of pulsars rotate around, and it tracks how the shape of each pulse changes as gravity bends the incoming light. The first NICA measurements in 2019 and subsequent years have given us some of our most precise measurements of neutron star radii, in the range of around 12 miles. There is another consequence of the gravitational lensing that is more dramatic. If the gravity is strong enough, light that grazes the surface of the star can be trapped in orbit around it for a moment before either escaping or falling back onto the surface. These temporary orbits create multiple images of the same feature on the star. In principle, you could see the same bright spot twice in different positions on the sky, one corresponding to the direct view and another corresponding to light that looped around once before escaping. The same phenomenon happens around black holes, but much more dramatically. Near a neutron star, it is subtle, a small correction that astronomers know how to account for. The deep takeaway is this: gravity does not just pull on matter, it bends the very paths that light takes through space. Near a dense enough object that bending becomes significant enough to reshape what you can see. Gravity is also doing something to time itself. Place a clock on the surface of a neutron star and another clock far away in space and let them tick. When you bring the surface clock back to safety and compare, you'll find it has fallen behind. It hasn't broken, it hasn't malfunctioned. It recorded fewer seconds than the distant clock because, in the strong gravity of the neutron star, time itself ran slower. This is gravitational time dilation, a consequence of Einstein's general relativity. The more intense the gravitational field, the slower time passes for an observer in that field. On Earth, the effect is tiny but measurable. Atomic clocks at sea level tick slightly slower than atomic clocks on mountain tops. GPS satellites have to correct for time dilation constantly, or your phone's location would drift by miles every day. Near a neutron star, the effect is not tiny at all. Standing on the surface of a typical neutron star, time would pass for you at roughly 70 to 80% of the rate it passes for someone watching from far away. For every 10 seconds that ticked on your wrist, maybe 13 or 14 ticked for the distant observer. A day for you would be more than a day for them. If you somehow lived for a year on the surface of a neutron star, 3 or 4 months of galactic time would pass beyond it. Though of course, no human could survive the gravity, or the radiation, or the magnetic field, or the dozens of other things that would kill you instantly. This is a thought experiment. The effect is measurable. When neutron stars in binary systems orbit each other, the light from their surfaces is shifted to longer wavelengths as it climbs out of the gravitational well. This gravitational redshift directly encodes the strength of the star's surface gravity. By measuring the shift, astronomers can determine the ratio of mass to radius for the star. Here's the picture that sticks. Imagine standing on the surface of a neutron star and watching the rest of the universe above you. The distant stars would appear to be moving strangely fast. Events unfolding in the galaxy around you would speed up visibly, the way a time-lapse video shows a flower blooming in seconds. You, standing still, would seem to the outside world to be frozen or slowed, moving through each gesture like a figure underwater. This is not an optical illusion. It is a real feature of the fabric of space and time near massive objects. Time is not a universal clock ticking at the same rate for everyone. It is a local quantity that depends on where you are and how deep in a gravity well you sit. And this effect gets more extreme the more massive the object. For a neutron star at the upper mass limit, time dilation at the surface can reach 40 or 50%. The tick of a second on the star is closer to 2 seconds outside. Go even denser, and you approach a black hole, where time dilation becomes infinite at the event horizon. In this sense, a neutron star is a bridge. It is the densest stable object in the universe, sitting one step away from a black hole on the ladder of compression. And the most dramatic event in neutron star astronomy happens when two of them meet. On August 17th, 2017, at 12:41 Coordinated Universal Time, a signal reached the LIGO gravitational wave detectors in Louisiana and Washington state. It was followed almost immediately by a similar signal at the Virgo detector in Italy. For the first time in human history, we had detected gravitational waves from the collision of two neutron stars. Gravitational waves are ripples in the fabric of space itself. When two massive objects spiral toward each other and merge, they shake space, sending waves outward at the speed of light. These waves had been predicted by Einstein in 1916. For a century, nobody could directly detect them, because the distortions they produce are smaller than the size of a proton over the length of a football field. In 2015, LIGO caught its first signal from the merger of two black holes. Over the next 2 years it caught more, but all of those were black hole mergers, invisible events producing no light. The 2017 event was different. Within seconds of the gravitational wave signal, a satellite called Fermi detected a burst of gamma rays coming from the same patch of sky. Telescopes around the world swung to that location, and over the following hours and days they saw a fading afterglow of light across every wavelength from radio to X-rays. The collision happened in a galaxy called NGC 4993, about 130 million light-years away. This signal had been travelling toward us since the age of dinosaurs. Here is what happened. Two neutron stars, each roughly 1.5 solar masses, had been orbiting each other for hundreds of millions of years. As they orbited, they radiated away their energy in gravitational waves. This caused their orbit to shrink, slowly at first, then faster, then catastrophically. In the final seconds before collision, they were orbiting each other hundreds of times per second, spiraling in toward each other at a significant fraction of the speed of light. Then they touched, and in a flash, they merged into a single object and released an enormous burst of energy. The merger produced about 2% of a solar mass worth of material flung outward at high speed. It produced gamma rays, X-rays, visible light, infrared, and radio waves in a cascade that played out over weeks. And it produced the gravitational wave signal that had alerted us in the first place. The combined signals, gravitational and electromagnetic, allowed astronomers to study the event in unprecedented detail. This was the first time humans had observed the same cosmic event with two completely different tools, one sensing vibrations in space itself, the other catching light. The event was given the name GW 170817, and it immediately became one of the most studied events in astronomy. Papers about it continue to be published years later, each one extracting new information from the data. It told us about the equation of state of neutron stars, about the physics of the strong force, about the origin of heavy elements, about the rate at which the universe is expanding. It also told us something specific and surprising, something about where gold and platinum come from. For decades, astronomers debated where the universe's heavy elements come from. Hydrogen and helium were forged in the Big Bang. Everything from carbon up to iron was produced inside stars through fusion and blasted across space when those stars died in supernovae. But iron is where stellar fusion stops. The elements heavier than iron, gold and silver and platinum and uranium, require a different process. They need a flood of neutrons, more than normal stellar environments can provide, to build up one atom at a time through rapid neutron capture. For years, the leading theory was that supernova produced these heavy elements, but careful calculations suggested that supernova might not be quite good enough. They produce some heavy elements, but maybe not enough to explain the abundance we actually see. Neutron star mergers were another candidate. A collision between two neutron stars would eject a large amount of neutron-rich material into space. That material would rapidly build up heavy elements through the same kind of neutron capture process. The question was whether these mergers happened often enough and produced enough material to account for what we see. The 2017 merger answered the question. As astronomers followed the afterglow of the collision in the days after detection, they saw something specific. The fading light had a distinctive signature of radioactive decay of heavy elements. The colours changed in a predictable way as the newly formed atoms settled into stable configurations. This signature had been theoretically predicted, and it matched the observations. From the brightness and duration of the afterglow, physicists estimated the total mass of heavy elements produced. The answer was roughly 10,000 times the mass of the Earth. In gold alone, the merger produced something like 100 Earth masses of gold, flung into interstellar space at a significant fraction of the speed of light. 100 Earth masses of gold from a single collision, scattered across the galaxy. Over billions of years, these mergers add up. Each one seeds the surrounding space with a rain of heavy elements. Those elements get incorporated into clouds of gas and dust, which eventually collapse to form new stars and planets. Some of the planets that form from that enriched material end up with gold and platinum and uranium in their crusts. Your wedding ring, if you have one, is made of atoms that were produced in the collision of two neutron stars sometime in the distant past, before our solar system existed. The same is true for every gold atom in every piece of jewellery, every circuit board, every tooth filling on Earth. The 2017 event was not a one-time discovery. It established a mechanism. Since then, astronomers have continued to search for more neutron star mergers, and a few candidate events have been detected, though none with the clear multi-messenger signature of the 2017 event. The implications stretch far beyond jewellery. Heavy elements are critical for biology, for technology, for the building of planets. Without neutron star mergers, the universe would have far less of the material we depend on. In some sense, the periodic table you learned in chemistry class is a partial record of what dying stars and colliding neutron stars have produced over billions of years. And the afterglow of that 2017 collision has a name. It's called a kilonova, and watching it unfold in real time was like witnessing a chemistry lab run on cosmic scales. In the hours following the August 2017 gravitational wave signal, telescopes around the world captured the fading light of the collision. What they saw was unlike any other transient event in astronomical catalogues. The afterglow was named a kilonova, from the Latin word for thousand, because it shone about 1,000 times brighter than an ordinary nova. But it was much dimmer than a full supernova, and it faded much faster. Over about a week, the light evolved through a characteristic sequence of colours. The first night after the merger, the glow was blue. Blue light comes from relatively cool, relatively transparent material, and it indicates that the ejected mass was mostly made of lighter, heavy elements, things like strontium and yttrium, which are around number 40 on the periodic table. By the third or fourth night, the colour had shifted to red and infrared. This shift indicates that the heavier elements, the lanthanides and actinides near the bottom of the periodic table, had started dominating the emission. These are elements like neodymium, europium and uranium. They absorb blue light very effectively, so once they are present in large quantities, the light that escapes is stretched toward longer wavelengths. This colour evolution was a direct chemical fingerprint of what was happening. Physicists could read the progression of elements being synthesized as the afterglow faded. It was the first time anyone had watched heavy element synthesis unfold in real time. The specific elements detected included strontium, confirmed by distinctive spectral lines. Strontium is used in fireworks on Earth, where it produces the bright red colour. It was detected in the 2017 event by absorption lines in the afterglow spectrum. It was the first time a heavy element had been definitively identified as coming from a neutron star merger. Other elements are harder to confirm spectrally, but the overall abundance pattern matches expectations from theoretical models of what should be produced in these events. Here's a picture that helps. Imagine a giant cloud of material being flung outward from the collision site at speeds of tens of thousands of miles per second. The cloud has layers with different compositions. The outer layers, moving fastest, are relatively poor in the heaviest elements. The inner layers, moving slightly slower, are full of lanthanides and actinides. As time passes, we see through deeper and deeper layers, and the composition of the light we receive shifts. Beyond the initial afterglow, the collision continued to shine in X-rays and radio waves for years. These long-lived signals come from the interaction between the ejected material and the surrounding interstellar gas. As the material slams into whatever is around it, shocks heat up the gas and produce ongoing emission. Astronomers were still detecting the radio afterglow years after the original event, each measurement refining our understanding of the collision's geometry and energy. The 2017 event has become a standard reference for understanding neutron star mergers. When future mergers are detected, they will be compared to this one. Aspects of the event that were unexpected, including the detailed shape of the gamma ray burst and the rise of the radio emission, have forced theorists to update their models. The remnant of the collision, the merged object left behind where the two neutron stars used to be, is itself a mystery. It could be an unusually heavy neutron star. It could be a very small black hole. It could have collapsed from one to the other during or shortly after the merger. What was left behind is a question physicists are still trying to answer. When the two neutron stars of GW 170817 collided, they produced an object right at the boundary of what is physically possible. The combined mass of the two stars was roughly 2.7 solar masses. Some of that mass was ejected in the kilonova, flung outward to seed space with heavy elements. The rest stayed behind, collapsing into a single compact remnant. The question is what that remnant is. Based on the dynamics of the collision, the remnant probably had a mass of about 2.6 solar masses, very close to the theoretical maximum for a neutron star. The exact maximum depends on the equation of state, which we still don't know precisely, but it is somewhere between 2 and 2.5 solar masses for a non-spinning star and a bit higher for one spinning rapidly. A remnant at 2.6 solar masses is in the borderline zone. It could be the heaviest neutron star ever observed, held up against gravity by the stiffest possible nuclear matter, and possibly by the centrifugal force of extreme rotation, or it could have already collapsed into a black hole. For the first fraction of a second, the remnant was certainly still a neutron star of some kind, a highly deformed, rapidly spinning, incredibly hot object that physicists call a hypermassive neutron star. This object was spinning so fast that centrifugal force was helping hold it up. It was emitting gravitational waves continuously as it oscillated and settled. As time passed, the hypermassive neutron star lost angular momentum, partly through gravitational wave emission and partly through dragging on the surrounding material. Without the support of rapid rotation, gravity would eventually win. The remnant would collapse into a black hole. The question is when, and whether the object we see today, whatever it is still a neutron star or has already collapsed. Analysis of the observations suggests the hypermassive neutron star phase lasted less than a second. After that, either the remnant collapsed into a black hole, or it settled into a stable neutron star that just happens to be at or near the theoretical maximum mass. The current best guess, based on the gravitational wave signal and the subsequent electromagnetic afterglow, is that the remnant eventually collapsed into a small black hole. But this is not certain. There is still active debate in the literature about the final fate. If the remnant is a stable neutron star, it is the heaviest ever observed, and it puts an important constraint on the equation of state of nuclear matter. If it is a black hole, it is one of the smallest ever observed, challenging previous ideas about the minimum mass at which black holes can form. Either outcome is consequential. This highlights a fundamental tension in neutron star physics. Ordinary stellar collapse is supposed to produce neutron stars up to some limit, and black holes above it. But neutron star mergers can produce remnants right in the uncertain zone between the two. These mergers are a natural probe of the transition between the two types of compact objects, and they may reveal whether there are intermediate states we have yet to recognize. Future gravitational wave detectors, more sensitive than the current generation, will be able to follow the post-merger oscillations of the remnant in detail. They will tell us how long the neutron star survived before collapsing if it did. They will give us direct information about the equation of state at densities beyond anything we can currently simulate. For now, we wait. And while we wait, the mystery of where all the neutron stars in our galaxy are hiding is turning up in unexpected places. Our galaxy has been busy for about 13 billion years. During that time, millions, probably hundreds of millions, of neutron stars have been born. Every massive star that has lived and died in the Milky Way should have left behind a neutron star or a black hole as its corpse. Yet when we look for them, we find strangely few. The confirmed population of neutron stars in our galaxy is somewhere around 3,000. That number keeps growing as surveys find more, but it is far below the theoretical expectation of tens or hundreds of millions. the vast majority of our galaxy's neutron stars have never been directly observed. Most of them are probably just invisible to us. Pulsars are easy to find if their beams happen to sweep across Earth, but we estimate only 1 in 10 neutron stars is a visible pulsar from our vantage point. The rest are too old, too cold, or pointed the wrong way. They exist. They just don't send us signals. Even accounting for this, the population we can detect is smaller than it should be, particularly in certain regions of the galaxy. One of the most puzzling cases is the centre of the Milky Way, near the supermassive black hole Sagittarius A star. The galactic centre is crowded with old massive stars. Over billions of years, these stars have been dying and leaving behind neutron stars. The region should be absolutely swarming with them. Thousands, maybe tens of thousands of pulsars should be detectable within a few dozen light years of the centre. Instead, there are only a handful. This is called the missing pulsar problem, and it has been bothering astronomers for years. Various explanations have been proposed. Maybe the extreme environment near the black hole disrupts pulsar formation. Maybe the intense gravitational field and strong magnetic forces scatter the pulses so much that they become undetectable from Earth. Maybe the actual formation rate of neutron stars in the galactic centre is lower than predicted for reasons we don't understand. A similar puzzle exists in globular clusters, dense balls of ancient stars orbiting our galaxy. These clusters have produced many neutron stars over their long histories, but the binary dynamics inside them are chaotic. Many neutron stars have likely been kicked out of their clusters through gravitational interactions, flung into intergalactic space where we cannot find them. There may also be neutron stars that never became pulsars at all. Stars whose magnetic fields are too weak, whose rotations slowed too quickly, or whose ejection kicks from their birth supernovae were so violent that they are now drifting through empty space far from any obvious origin point. Some neutron stars have even been detected indirectly, through the gravity they exert on visible stars. A normal star in a binary system with an invisible companion can sometimes reveal the companion through its orbital motion. These measurements have turned up isolated neutron stars that would otherwise be impossible to find. The missing neutron star problem tells us our understanding of the galactic population is incomplete. We know these stars exist in huge numbers. We just can't see most of them. They're out there in the dark, cooling down, fading, invisible to the telescopes we have. But the ones we can see keep surprising us. Some of them do things pulsars aren't supposed to do. We talked earlier about pulsar glitches, those tiny sudden speed-ups where a neutron star briefly ticks faster than it should before settling back down. These events are rare. A typical pulsar might glitch once a decade, or not at all over a human lifetime, but they are extraordinarily informative. The size of a glitch tells us about the interior of the star. Small glitches, 1 part in a billion or so, are common in young, active pulsars. Large glitches, 1 part in a million, are rare and tend to occur in specific pulsars with particular histories. The timing of a glitch also matters. After the sudden spike, the spin rate doesn't immediately return to the smooth slowdown. It relaxes back over days or weeks following a specific pattern. That relaxation curve is a window into the physics of the star's interior. Consider the Vela pulsar, one of the most studied objects in the sky. Vela glitches roughly every 3 years, each time speeding up by about 1 part in a million. After each glitch, Vela relaxes over the course of weeks, with the curve showing multiple different timescales. One component of the relaxation is fast, a few days. Another is slow, a few weeks. A third might extend for years. Each timescale corresponds to a different process happening somewhere inside the star. The fast components suggest coupling between the superfluid and the crust. The slow components suggest deeper interior dynamics, possibly involving the core. By carefully modelling these timescales, physicists can test different pictures of the star's interior. Some models predict specific relaxation patterns that match the data well. Others predict patterns that don't match at all and can be ruled out. In 2016, an analysis of Vela's glitch behaviour suggested that the superfluid inside the star was unable to carry as much of the total moment of inertia as theorists had previously assumed. This had implications for how much of the star is actually in the superfluid state versus other phases. It helped constrain theories of Pastor layers and quark cores. More recently, observations with higher time resolution have revealed that some glitches show internal substructure. The spin-up isn't instantaneous. It happens over a fraction of a second, with detectable smaller events leading up to the main glitch. Observations of Vela in 2019 caught one of its glitches in progress for the first time, showing that the spin-up took about 12 milliseconds to complete and included multiple sub-events. This kind of detail is hard to explain without invoking specific models of vortex motion in the superfluid. The vortices we discussed earlier, those microscopic tornadoes in the neutron superfluid, must be rearranging themselves in cascades that collectively produce the observed spin-up. Glitches are not the only strange timing behaviour pulsars show. Some pulsars exhibit slow wander in their spin rates that cannot be explained by simple slowdown. Others show correlations between their radio brightness and their spin frequency. Each of these behaviours is a clue about what's happening inside. There are also pulsars that do something even more startling. They turn off. Some pulsars disappear. One day they are ticking along, sending their regular radio pulses to Earth. The next day, the signal is gone. A few weeks later, it comes back. Sometimes the switch happens suddenly. Sometimes it takes a few hours to fade out and a few hours to return. These are called intermittent pulsars, and they are one of the stranger phenomena in neutron star astronomy. The first clearly documented intermittent pulsar was PSRB 1931+24, discovered to be switching off for about a month at a time, then switching back on for about a week. The pattern repeats, though not with perfect regularity. During the off phase, the pulsar is completely invisible in radio waves. During the on phase, it looks like a normal pulsar. What's puzzling is that the off phases aren't just quiet. They're accompanied by a change in the star's spin-down rate. When the pulsar is active, it slows down at one rate. When it is off, it slows down more slowly, as if something that was applying braking torque has been removed. This tells us that the radio emission is tied to the same process that slows the star down. When the pulsar is emitting, it is losing energy through both radio waves and other radiation. When it is silent, the total energy loss is lower, suggesting that the emission mechanism itself has shut off. Nobody fully understands what causes the switch. One leading idea is that the magnetosphere, the region of space around the star filled with charged particles and trapped radiation, is capable of existing in two different states. One state supports active pulsar emission. The other is a quiet state where the emission is suppressed. The star flips between the two configurations on timescales of days or months, possibly triggered by changes in the charged particle population in the magnetosphere. Another idea is that the switch is caused by changes on the surface of the star itself. A slight rearrangement of surface currents or small-scale magnetic field lines could be enough to turn the emission off and on. Beyond intermittent pulsars, there is a related phenomenon called nulling. Some pulsars show occasional missed pulses where 1 or 2 rotations in a sequence don't produce a detectable flash. The star keeps spinning, but the beam skips its appointed flash and then returns. Nulling can range from occasional single missed pulses to long stretches where most pulses are missing. Yet another category is called rotating radio transients, or RRATs. These are neutron stars that occasionally emit very strong single radio pulses separated by long silent intervals. An RRAT might emit 1 bright pulse per hour or per day, with nothing in between. If these objects were spinning more slowly, they might be mistaken for completely different types of transient sources. All of these behaviors, the glitches and the nulls and the intermittents, tell us that the magnetospheres of neutron stars are dynamic, complicated, and not at all well understood. The simple lighthouse model, where a steady beam sweeps from the surface, is a useful cartoon, but it hides a lot of complexity. And even as we try to understand the ordinary pulsars, theorists have predicted objects that are even stranger. Objects that are neither neutron stars nor black holes, but something in between. Between a neutron star and a black hole lies a theoretical object called a quark star. A quark star is a hypothetical compact object made entirely of quark matter. We discussed earlier how the core of a sufficiently massive neutron star might contain a region of deconfined quarks. A quark star would be a star where the entire interior, or nearly all of it, is in the quark matter state. Not just a small core surrounded by ordinary neutron matter, but a full ball of quark soup from surface to center. Quark stars would form if strange quark matter is stable, or if certain theoretical conditions are met during the collapse of very massive stars. In some scenarios, a neutron star at the upper mass limit might convert into a quark star if a seed of strange matter forms in its core and spreads throughout the star. This conversion would release a burst of energy and neutrinos, similar to a supernova but with a different signature. From the outside, a quark star would be similar to a neutron star in rough properties. Similar mass, similar size, similar surface temperature. The differences are subtle but potentially detectable with enough data. A quark star might be slightly more compact than a neutron star of the same mass, meaning a smaller radius. It might cool differently over time. Its equation of state would be different enough that gravitational waves from a quark star merger should look different from a neutron star merger. There are currently a handful of candidate objects that may be quark stars, though none has been confirmed. Some neutron star observations are best fit by models that include a large quark core or are fully quark. In particular, objects with masses near the upper limit, 2.1 or 2.2 solar masses, where the internal pressure is at its highest, are prime candidates for hosting substantial quark matter. The difficulty of confirming a quark star comes down to measurement precision. To distinguish a quark star from a neutron star of the same mass, you need to measure the radius to within a mile or two, and to measure the tidal response during a merger very precisely. Current observations are close to this level of precision, but not quite there. The next generation of gravitational wave detectors, including instruments like the Einstein Telescope and Cosmic Explorer, should be able to distinguish quark stars from neutron stars directly. There is also a more exotic class of objects called hybrid stars, which sit between neutron stars and quark stars. A hybrid star has an ordinary neutron matter exterior, a transition region, and a quark matter core. The proportions and boundary conditions determine whether the star behaves more like a neutron star or a quark star from the outside. The physics of quark stars gets even stranger. when you consider the possibility of color superconducting cores, which we mentioned earlier. A quark star with a CFL core would have an even more exotic interior, with quarks locked in coordinated patterns throughout much of its volume. The detailed structure of these stars requires solving problems in quantum chromodynamics that are currently beyond our computational abilities. One of the most intriguing aspects of quark stars is that they could potentially be smaller than the smallest stable neutron stars. A quark star might have a mass as low as 1/10 of a solar mass and still be stable, whereas a neutron star with that mass would not hold together. If low-mass quark stars exist, they would be a new class of compact object entirely. And just beyond quark stars on the mass ladder lies the most extreme compact object in the universe. Just above the mass limit of whatever exotic matter holds up the heaviest neutron stars, gravity finally wins. The star collapses into a black hole. What does that transition look like? What happens at the exact moment an object crosses from being almost a black hole to being a black hole? The short answer is that from the outside the transition is smooth. A star at the maximum mass has extreme gravity, gravitational redshift and time dilation. A slightly heavier star collapses into a black hole with only slightly more extreme versions of these effects right at the event horizon. The transition isn't dramatic in terms of external appearance. What changes is that once the event horizon forms, no signal can escape from within it. Before the horizon forms, light can still climb out of the gravity well, heavily redshifted but not infinitely so. Photons emitted from the surface of an almost black hole star arrive at a distant observer with reduced energy and reduced frequency, but they still arrive. After the horizon forms, light emitted from the would-be surface stops reaching the outside universe. The surface itself becomes inaccessible. This suggests an interesting possibility. What if there are objects in the universe that are compact enough to be extremely black hole-like, but don't actually have event horizons? Various theoretical proposals for such objects exist under names like graver stars, fuzzballs, and black stars. These are speculative ideas, and most physicists think actual black holes probably do form as general relativity predicts. But the possibility of horizonless compact objects has not been entirely ruled out by observations. If such objects exist, they would sit right at the boundary we've been exploring. They would be the absolute limit of compression without collapsing into a true black hole. Gravitational wave observations of compact object mergers have started to put constraints on these alternatives. The gravitational wave signal from a merger has a characteristic pattern that depends on the nature of the objects involved. Black holes produce a specific ring-down signal. Other objects would ring down differently. So far, the observed mergers are consistent with black holes, but more sensitive observations may eventually reveal deviations if horizonless alternatives exist. For neutron stars specifically, we know they have surfaces. Observations of their thermal emission, their X-ray bursts, and their crust-related dynamics all require a solid surface at the top of the star. There is no question that neutron stars are real and have physical boundaries. What's uncertain is what happens between the heaviest neutron star and the lightest black hole. There is a gap in observed masses, roughly from 2.5 to 5 solar masses, where very few objects are found. Whether this gap is real or just an observational artifact is still debated. If it's real, there might be some astrophysical process that prevents formation of compact objects in this mass range. If it's not, there might be a population of objects hiding in the gap that we haven't yet detected. The compact object formed in the GW 170817 merger, as we discussed, sits right in this gap. Whether it's an ultra-heavy neutron star, a black hole, or something else entirely is one of the open questions in the field. And underlying all of these questions, all of these models, all of these measurements, is a single, unresolved theoretical problem. We don't really know the equation of state. Everything we've discussed about neutron stars depends on one crucial function. It's called the equation of state, and it describes how the pressure inside the star depends on the density. The equation of state is what tells you how stiff the matter is. If you push on a chunk of nuclear matter with a certain force, how much does it compress? That relationship, expressed mathematically, determines everything else about the star. It determines the maximum mass. It determines the radius as a function of mass. It determines how the star cools, how it oscillates, how it merges, how it responds to the tidal pull of a companion. For ordinary materials, equations of state are well known. Water, air, metals, rocks. We have measured their compressibility at various pressures and temperatures. We know how they respond because we can put them in lab equipment and squeeze them. For nuclear matter at the densities found inside neutron stars, we cannot do this. The pressures involved are trillions of times higher than anything we can produce on Earth, even briefly. We have no way to directly measure what happens, so instead, physicists build theoretical models. They take what we know about nuclear physics from laboratory experiments at lower densities, and they extrapolate to the extreme conditions inside neutron stars. Different theoretical approaches give different predictions, and there is no universal agreement on which approach is most accurate. Some equations of state are stiff. They predict that matter resists compression strongly, which means stars can hold more mass before collapsing, and their radii tend to be larger for a given mass. Other equations of state are soft. They predict that matter compresses more easily, which means lower maximum masses and smaller radii. For decades, we didn't have enough observational data to distinguish between these competing predictions. Then measurements of neutron star masses and radii started to accumulate. The discovery of neutron stars with masses around 2 solar masses ruled out the softest equations of state. They simply can't support that much mass. This was a significant step forward. The nicer radius measurements have further narrowed the possibilities by constraining how large neutron stars of known mass actually are. The gravitational wave observations from GW 170817 added yet more constraints by measuring how much the neutron stars deformed each other in the final seconds before merger. Slowly, the range of viable equations of state has been shrinking. The current state of the field is that we have bracketed the true answer to within a relatively narrow band, but we still have multiple competing theoretical models that all fit the data. Part of the uncertainty comes from the possibility of phase transitions inside the star. The equation of state for pure neutron matter is one thing. If there is a transition to quark matter partway through the core, the equation of state changes at that point, producing a kink in the overall relationship. Depending on the sharpness of the transition, this kink could be subtle or sudden, and it could affect the star's properties in different ways. The ultimate test will be more observations. Future gravitational wave detectors will catch many more neutron star mergers, each one providing independent information about the equation of state. X-ray telescopes are continuing to refine mass and radius measurements. As the data accumulates, the true equation of state should emerge from the crowd of candidates. And as one example of what careful observations can reveal, consider what a single X-ray telescope on the space station has already taught us. In June 2017, a refrigerator-sized instrument was shipped to the International Space Station and mounted on its exterior. Its official name is the Neutron Star Interior Composition Explorer, which is usually shortened to NISA. NISA is an X-ray telescope designed for a specific purpose. It watches the bright hot spots on the surface of pulsars, and it measures how the X-rays from those spots change as the pulsar rotates. The goal is to map the size and shape of the emission regions with enough precision to determine the neutron star's mass and radius. This works because of gravitational light bending. We discussed earlier how the gravity of a neutron star bends light from the surface, making parts of the back of the star visible from certain angles. The amount of bending depends on the ratio of mass to radius. By watching how a hotspot's X-ray light changes as it rotates in and out of view, and how much distortion the light experiences, NISA can extract very precise constraints on both mass and radius simultaneously. In 2019, NICER published its first detailed measurement of a specific pulsar called PSRJ0030+0451. The target was a millisecond pulsar rotating about 200 times per second, close enough to Earth for detailed observations. The analysis determined its mass to be about 1.5 solar masses and its radius to be about 8 miles, with precision better than about 1 mile in each direction. Those measurements immediately ruled out several equation of state candidates and sharpened the range of viable alternatives. Further NISA measurements of additional pulsars have continued to refine our understanding. One result has been particularly striking. The data suggest that neutron stars with very different masses have roughly similar radii, around 12 kilometers. Lighter stars and heavier stars seem to converge on a similar size. This is a specific and unexpected behavior that constrains the equation of state significantly. Another result from NICER is a detailed map of the hotspot patterns on pulsar surfaces. These maps are the first detailed topography of neutron star surfaces that have ever been made. They reveal that the magnetic field geometry near the surface is more complicated than simple models suggested. Instead of two neat dipolar poles, the actual hotspot patterns often show offset, distorted, and multi-component structures. This means the magnetic field of a neutron star near the surface is messy. Small-scale features and complex shapes exist alongside the large-scale dipole. This changes our understanding of how pulsar emission works and what the surface conditions are. NISA is just one instrument. Other X-ray telescopes, radio telescopes, optical telescopes, and gravitational wave detectors are all contributing pieces of the puzzle. Together they're building a coherent picture of what neutron stars are, how they behave, and what they tell us about fundamental physics. Every new measurement refines the picture a little more. Every new piece of data either confirms or challenges existing theories. The field is in a golden age, where observations are finally detailed enough to distinguish between long-debated theoretical possibilities. And all of this work, all of this careful measurement and modelling, points toward a larger truth about why neutron stars matter so much. Every particle accelerator on Earth, every high-pressure diamond anvil cell, every neutron source, every magnetic field generator we've ever constructed falls short of the conditions inside a neutron star. The highest pressures we can achieve on Earth briefly in devices like diamond anvil cells are around 5 million times atmospheric pressure. That's enough to compress ordinary matter into unusual forms. It's enough to study how minerals behave inside the cores of rocky planets. It's about 1 trillion times weaker than the pressure inside a neutron star core. The strongest magnetic fields ever produced in laboratories are around 1 million Gauss, sustained for microseconds. The field of a magnetar is 1 billion times stronger, sustained for millions of years. The highest temperatures we can produce in laboratories, in specialized facilities studying quark-gluon plasma, reach a few trillion degrees for a few trillionths of a second before dispersing. The interior of a newly formed neutron star is hotter than that, and it stays that way for much longer. We cannot build a neutron star. We cannot even build something remotely like one. The conditions that exist inside these objects, the pressures and densities and magnetic fields, cannot be produced in any form we can currently imagine. If we want to study physics at these extremes, we have to observe neutron stars and learn from them. This makes neutron stars a unique kind of laboratory. They are natural experiments in fundamental physics, running continuously for billions of years, each one producing observable consequences that we can detect with telescopes and gravitational wave detectors. What physics do neutron stars test? A lot. They test nuclear physics at densities far beyond anything we can reach in particle accelerators. The equation of state, as we've discussed, constrains how the strong force behaves under extreme compression. The existence or absence of quark matter cores tests our understanding of quantum chromodynamics, the theory of how quarks and gluons interact. They test general relativity and strong gravitational fields. The gravity around a neutron star is a significant fraction of what it would take to form a black hole, which makes it the strongest gravity we can directly study at a surface we can see. Effects like gravitational redshift, frame dragging, and light bending all have specific predictions in general relativity, and neutron stars let us verify those predictions. They test quantum electrodynamics in extreme magnetic fields. The magnetofields we've discussed are strong enough that vacuum itself becomes birefringent, and light polarization behaves in unusual ways. This has been experimentally verified by polarization measurements of magnetaire emission, confirming predictions from decades ago. They test models of dense matter at temperatures and densities relevant to the earliest moments of the universe. The color superconducting phases that may exist inside the cores of neutron stars are relevant to understanding how matter behaved microseconds after the Big Bang, when similar conditions existed throughout space. Every time we make a more precise measurement of a neutron star, we're doing physics that cannot be done any other way. Every time we detect a new neutron star merger, every time an X-ray telescope maps a pulsar surface, every time a gravitational wave detector catches a signal from deep in space, we learn something about fundamental laws of nature. The next generation of detectors will be far more sensitive. Observatories planned for the next decade will catch hundreds of neutron star mergers per year. New X-ray missions will map more pulsar surfaces with higher precision. New radio surveys will find many more pulsars. Theoretical models will be tested and refined and tested again. We'll keep learning from these compact objects for as long as we keep looking. A teaspoon of matter, heavier than a mountain range, sitting out in the dark, quietly showing us what the universe can do when it pushes matter to its absolute limit. Somewhere in our galaxy, a neutron star is ticking.